speaker. He's a first-year PhD student in mechanical engineering at Berkeley, where he works in the Berkeley Fire Research Lab. His research focuses on high-performance scientific computing and wildfire studies, developing simulation tools to better understand how destructive fires spread across landscapes and into communities. Adam graduated with distinction from the University of Kansas with a bachelor's degree in mechanical engineering and a minor in mathematics. His undergraduate work focused on computational fluid dynamics and numerical methods applied to problems in chemically reactive flows. At Berkeley, he contributes to the open source ELMFIRE wildfire modeling software, developing verification and validation, and incorporating new physics models for urban fire spread and suppression. Beyond research, he is also active in mentoring and outreach, and is passionate about accessible STEM education to broader audiences. And despite working in combustion and fire sciences, Adam has nearly burned down his apartment 3 times in the past 4 months. And probably shouldn't be trusted near open flames, but we trust with them all. Yes.
Thank you very much for that introduction. And thank you again to the Compass Lecture for setting this up, and the free food. That's always appreciated. Yeah, no, the almost burning my house down is absolutely true. I'm still getting used to gas stoves, but I'm a little bit more tame in the lab. So today I want to be talking about, I've only been here for maybe 5 months now. So I don't have a whole lot of research to show, but I really wanted to kind of go over how much I've learned. So at KU, I was really focused on those chemically reacting flows. And I thought, well, combustion and fire, these are like the same thing, right? So everything should be very consistent here. I learned that was not very true, and that we have a lot more open questions in fire than we do in combustion. So really my 4 questions that I want to kind of pose and try to answer in this talk is, why do we care about fires? What even is fire? How can we model it, and how do we model it, or how do we model it here? So first up, why do we care? This one might be obvious. Who's a California native? Okay, almost everybody. Okay, so in Kansas, we don't have a whole lot of wildfires. We have prepared fires for like fields and stuff, like prescribed burns. In California, especially, what we have is the wildland urban interface. Has anybody heard this term? Okay, so the definition is kind of broad, but really it's wherever humans and their development meet or intermix with wildland fuel. So if we have this spectrum from wildland, it's just like just the forest and the trees, and all the way over to the urban areas where it's just houses and development, wildland urban interface, or WUI, is somewhere in this region. And we care a lot about this, especially when we're modeling things and preparing for fires, because this is right when the human interaction starts to happen and where we get our destructive fires that start to burn down our communities. Fires off in the wildland are good and they're healthy and they're great for fire ecology, but we don't want to be burning down people's homes, and we don't want people to die. And how much of our land actually is considered this WUI? So here's a nice graph I found. The darker areas are like the higher ones. So this is the proportion of homes in the WUI, people in the WUI area. And in fact, we're projected to, in the Western United States, roughly 50% of the future development is going to be in these WUI areas. And we have a lot of problems when it comes to fires in these areas. We only have so many resources, like firefighting resources, but this large land area. So where do our people go? What houses do we protect, and which ones do we kind of sacrifice? And what about evacuation of people from these areas? If there was a fire started in the Berkeley Hills, for example, it's estimated it may take like 4 hours for one person to evacuate. So time absolutely matters. And so our preparation and planning, but also forecasting also matters. And this is where kind of our fire modeling comes into play. Now, the government loves to talk about budgets and money. What is costing me money here? 2 really cool plots. This one is the number of fires over time from 1985 to 2015, we see that roughly the same amount of fires are happening every year. But if you notice this other side, the area burned is exploding. It's a large amount, and you can kind of correlate this to the structures lost. So we see the same amount of fires that are occurring, but they're going to be much more disastrous fires when they do happen. So initial attack suppression efforts, like the aerial drops from firefighters or ground troops, this stops about 97% of our fires, but those last 3% are what kind of explode into these mega fires that we see. You can kind of think of it as like hand sanitizer, so 99.9% effective, but like the 0.1% is the really bad stuff. And then over here, we can see the federal suppression costs. So it was pretty low, and it's continuing to blow up again when we start to see these very large mega fires. And it's projected to quickly exceed the budget for the entire United States Forestry Service. It's projected to be like $4.3 billion annually. This is another nice price tag plot that I found. These are all like the biggest fires in California. I'm sure you guys are familiar. And this is like the estimate of how much of this is costing like the local economy. So this is now, we're not only getting into how much the government is spending on this, but how much are people spending on like rebuilding homes or evacuating and things like this. So a little bit more motivation. It's not just a California problem, it's a world problem. I found this, there's a website where you can get the hazard likelihood of anywhere in the United States. This is the Bay Area. Red means very high hazard, which means should a fire start there, it's a very high likelihood that it's going to be disastrous. And then yellow is like the least severe. But the whole area, the whole map is lit up except for where the water is. So everything is very burnable. We're actually doing pretty well in the US in terms of like suppressing fires. Canada has a much bigger problem because there's a lot more forest area. This is another huge problem in South America and in Africa and like Portugal and Spain. It's really a global problem. And of course, it wouldn't be a fire talk if we didn't get to see some fire. So these are our biggest fires in California: Camp, Glass, Kincaid, Tubbs, Thomas, now our Eaton and Palisades fires. But it also happens in Australia. I thought this was really interesting. They call them bushfires. And then this is also in China. Now, when these fires happen, it's not just this was caught on fire, this burns. There's other things that are happening as well. Like everything that's being released from these fires. Let's think about like the chemistry involved, especially when we're burning houses. You would be really surprised what kind of nasty stuff comes out of burning, like your toilet, for example, or the pipes in your house. Things like they're called volatile organic compounds, and also heavy metals. These can be transported miles away to other communities where it can cause like really bad air pollution days. Okay, so we've identified that this is a problem. I want to kind of study it and model it. What even is fire? So what is fire really? Fire is a chemical and physical phenomenon. Something that is really canonical in the wildfire literature is this called the fire triangle. So you need three primary components: the fuel, oxygen, and heat. If you remove any one of these, then the fire goes away. Now, importantly, when we are in these large fire situations, the majority of what's burning this is called solid phase combustion. You can only combust vapors. Only vapors are combustible. If you do not believe me, I have a professor who used to say this: take a match and take a large barrel of gasoline and very quickly extinguish the match in the gasoline. Don't actually try it. This is not safe, but you can't burn a liquid. You cannot burn a solid. You can only burn a gas. And so there's a chemical or thermal decomposition of the material into something that can be burned, starting from evaporation of all the moisture that's in there, torrefaction, which is like the separation of the liquid components, like the oils, pyrolysis, which is the changing of the solid material into combustible vapors, Gasification is like the secondary stage of that, where you get what's called syngas, which is also combustible. And then if you get it hot enough with high enough temperatures and pressures, eventually you get combustion or an explosion, which is just rapid exothermic reactions. And fire is this that's able to self-sustain or self-heat. How does fire interact with other things? So when we look at fires, you're not actually looking at the fire. What you're actually looking at is the extremely hot soot or hydrocarbon chemicals that are being produced. They're glowing red hot, like steel would glow red hot. And this is actually the orange and yellow colors that we see in fire. Now we have a really hot vapor that's coming out, and hot air rises. The relatively cold air is falling, and it produces this buoyancy effect. This is extremely predominant. And if you look in microgravity combustion, for example, you get like a spherical flame because the buoyancy effects are null. And then also we can kind of think of this as its own bulk fluid. So interactions with the surrounding bulk fluid also affects the shape, and it also affects like the height of everything. So as more air comes into it or more oxygen comes into it, we're allowed to combust more, which increases the height of the flame. And you can think back to the fire triangle on that, right? You need three things. Okay, so that's what happens at the small scale. What happens at the very large scale when we're talking about the WUI now? So three primary mechanisms are responsible for the spread of fires from structure to structure or in the WUI. This is direct flame contact. This is literally the fire object touching another object that's combustible. And it's heated through convection and conduction. Radiation allows for spread across discontinuous fuels, which is what we have in urban environments. There's like a road that is burnable technically, but it would take a long time. So radiation can be dominant in some situations. And then firebrands, this is like the little chunks of wood or vegetation and things that are broken off by the wind, and they can be carried miles and miles away and start new fires if they land in like a bush or some easily flammable material. So this is when we get to the part where experiment and theory is really important. What are the relative contributions of these modes? So I've identified these three primary modes. Which one do you think is most dominant? And it really depends. And this is an active investigation area. We don't really know. The direct flame contact, the convective impact of the fires is oftentimes completely counteracted by convective cooling of the wind surrounding it. Radiation, you would think would be pretty dominant, but also think back to like your Boltzmann constant, it's like really small. So maybe radiation is not very contributing. Firebrands are pretty direct. We literally have a small fire that is now touching other things and it's contributing, but also if we measure the radiation and conductive heat transfer from those, it also doesn't seem like it should be enough to heat. So this gets into a fundamental question that we really don't understand how fire spreads in these large environments. We understand it really well when it's happening in a combustion engine, but we don't really know it for this large scale. And I think this is really interesting, and this highlights why we need to continue doing experiments and understanding the underlying theory. I want to talk a little bit more about firebrands. These can structure destruction in these large-scale fires. In some cases, can be attributed 50% to these firebrands. So they're a very dominant factor. They're just, like I said, the small burning pieces that are broken off. There's kind of three phases. The firebrands are generated from like breaking off of a structure. They're carried by that plume. Remember the buoyant motion that's happening. They're transported across the wind, and these can go seriously miles to hundreds of miles away. And the speed at which that happens is on the order of the wind gusts that are occurring. I have the pretty cool video So we don't often get to run these big experiments, but this is coming out of the Insurance Institute for Business and Home Safety, IBHS, where they built up small, they're called accessory dwelling units. They're basically like shed homes, and they lit them on fire. And what we see here, like all these pieces that are flying into the camera, each one of these is a firebrand. So every structure that's burning is producing tens of thousands, hundreds of thousands of these particles. And when we look at the different or the relative sizes of these firebrands, they can be anywhere from like basically nothing all the way up to like the size of a plate. It just really depends on what's breaking off. Like if a shingle, for example, is broken off and carried away, then that may be larger and able to hold structure more. And so we think about how can we protect homes from these fires and the spotting, especially if we maybe reduce the amount of vegetation or combustible material that's near my house, then there's less things to ignite by these spot fires. And when we see development in urban areas or spread through like strictly urban areas, like for example, in the Tubbs fire, we see that this is a huge dominating factor that if the structures were to be less ignitable in the local areas, then we could have seen a lot less destruction. I want to talk a little bit about modeling goals. So we have a better understanding of how things are being spread, but we still have those open questions. But I have problems right now. I have fires that are burning right now. I just looked this morning and I think there were 3 fires that are actively burning in the United States that are like actively being attacked and trying to suppress. So that theory and the experiments, they help us understand why fires start, how fires spread, and how they cause damage. But we really need tools right now for answering these questions, which is, can we estimate risk maps of communities for fires to generate and spread, like what I showed earlier, those hazard maps? Can we predict and forecast active fires? Like, can we, where you would get your normal weather report, can you also get like a fire report? And then also, can we determine effective suppression mitigation strategies? Like, how can I protect my homes before the fire happens? And then also, how can I better stop the fires once they start? Over here, this is an example of an aerial suppression drop map. So each of one of these lines is like a pass that a specific aircraft went through and dropped like fire retardant or water. And there's all these different aircrafts that we have, and there's all these different areas. Now, the likelihood of a successful drop really depends on the fire intensity, the area coverage, the winds. So we need we need to know the ground conditions, and we can't have the entire U.S. Forestry Service on the ground covering that whole perimeter. So we have to be very strategic about where we're dropping things and understanding what the ground conditions are. And one way of doing this is computational modeling, where we're able to track fire fronts and we can calculate arrival times. We can estimate the radiative heat transfer coming from, or the fire line intensity that's coming from these, where the fire is at. Okay, so how can we model it? Here's one approach. This is from Fire Dynamics Simulator, which is like a CFD-based solver for modeling fire spread. Notice up here, simple chemistry. Okay, I don't think it's simple. But they say, okay, I'm just going to break down the fuel into carbon, hydrogen, oxygen, nitrogen, and not care about the molecular structure of it, just some like approximate values. I'm going to say, yeah, those are probably the important parts of my air is the oxygen and the nitrogen and maybe the CO2. And then it just happens to be all coming into soot and carbon dioxide and water. But we know that's not true. If you look at like the difference in the chemical structure of the same tree, but different parts of the tree, or even the same like style of tree in the same woodland area, but the different species, the chemical structure is entirely different. And then also the physical structure is entirely different. You may have different porosities that'll impact the spread rate and the likelihood of it being burned. So this is going into like fire ecology, where we're now talking with the plant biologists and all this stuff. And then everything else you may have seen: species transport, some equations in state like ideal gas law, energy, momentum, heat release, constitutive relationships. So we find the stress. This doesn't get it all. You also need to include closure relations, boundary conditions, and you need to numerically approximate this. And this still doesn't get everything. So Fire Dynamics Simulator has their complex chemistry model. If you look at the combustion of just H2, there's something like 23 simple steps or 50 complex steps in the chemical reaction or the chemical mechanisms that are happening. We're burning stuff that's way crazier than that. And then also think about how much input information do you think I need? We have buoyancy force, we need to know the temperature, we need to know the pressure everywhere. We simply don't have that information. This is not practical. How about no? Another challenge that we have is when we get to this large scale, we have this problem of relative scales. So combustion reactions are occurring at the molecular scale, but my communities are in the measures of like kilometers or tens of kilometers. And so what size do I put my mesh, my computational mesh? What parts do I just forget about? And this is not only in the spatial dimension, but also in the time scales. Combustion reactions are extremely fast. That's why they're combusting, and there's all that heat release. But the time that it takes a plume, for example, to rise and then transport can be like orders of magnitude larger. So we have to sacrifice some information. We have to say at some scale, we're just going to give up and assume that everything is nice and easy. Another challenge that we have is the data availability. So some of the data that we need when we're modeling stuff is the fuel information, so we can calculate that chemistry. We also need the moisture content, which is drastically affecting the how much heat release is available. We also need the wind data, so we know how quickly it's being pushed, so it affects like the flame geometry. We also need the topography. And here's an example of this has happened. These maps were constructed like months after these events, and they give a really nice description of approximate locations of where the fire started. And then these are, at best, hourly locations of where the fire line is. And what do you think the resolution of this is, of these fire lines are? And is it matching the scale of what we talked about previously? This is not down to the molecular scale and their accuracy. So this is a huge issue. Now, thankfully, we have some information. So starting in the 70s and 80s, there was a government level standard classification of fuels. It started off as 13 distinct categories, and it's been extended in the early 2000s to 40 distinct categories. But again, if we look at the burning of two different species of plant or tree or anything, we're getting drastically different results. So do we think that 40 different fuel classifications is good enough? And to clarify, these fuel classifications are like rock, grass, large grass, bush. Another thing that's good to note here is it would take forever to have somebody physically go into the field and say, that's a rock there. So they have to be specific about the resolution of the data. So standard is 30 meters. Now in 30 meters, I could have a whole lot of stuff happen in that. And especially when we get into urban areas, 30 meters is like, that can be your house and some of somebody else's house if you're really densely packed. It could be totally different. And to clarify, in the 40 fire behavior fuel model, which is what this is called, their classification for structure is non-burnable. It's absolutely burnable. We saw that earlier. So this is another challenge. We have some weather data also. So this is taken from a website called Firecast, which is like the forecasting that we can do. So this is some fine dead fuel moisture. That's another thing I forgot to mention. Even if you have the same species of plant, it burns completely different whether it's dead or alive, even with the same amount of moisture content. We don't really know why. But we get some pretty rough approximation or resolutions of this data. So, and when we look at the wind speed available, it's on the scale of like 2 kilometers, as we say. This is over this entire 2 kilometer area, it's the same wind speed and the same wind direction. We know that's absolutely not true. Also, when we get to the ground where the fire is, you see like vorticities that are occurring, vortexes occurring if you have wind moving through or past blunt objects, right? So, okay, that high fidelity approach was way too much. I'm going to go swing the complete opposite direction, and I'm just going to do some basic experiments, and I'm going to pull some curve fits, and I'm going to just apply it pretty broadly. And so this is what the operational models are. This came out of like the 70s and 80s from the US Forestry Service. These are semi-empirical and empirical models. They're designed to be quick and dirty. Now, as an engineer, I like quick and dirty. I can solve problems. So in 1972, this was the Rothermel model. This is extremely popular. And it's a 1D model for fire spread, and it assumes steady spread of the fire, which is not true. It has this term up here, which is kind of a ratio of the heat received through conduction, convection, radiation, and then also the likelihood of ignition or the amount of heat transfer required for that ignition. Think back to like the thermal decomposition of the log. That's what the QIG is talking about. And then it also says, we also need to include wind and slope, and I'm going to assume that they are mutually exclusive, and I can just add them together, kind of these correction factors. And Mark Finney is a guy over at the Missoula Fire Sciences Lab up in Montana. He's very popular in our field, and he said, it's not because it's right, but it's because it's useful. This is still widely used in our training for fire response. It's also used in the vast majority of current models, like our operational models. There's an equivalent for urban fire spread. This is the Hamada model. This is coming out of Japan. They were looking at, this is a pure empirical fit to data that's looking at spread from structure to structure in fire following earthquake, which is a whole separate field in civil engineering if you want to talk to them about it. It's really fast, but it's not that accurate. So this is a modern study that was done in 2024 or something like this. This is a lot of the data that was originally used to fit the Hamada model, and the line of perfect agreement makes sense. This is what they fit their data to. But these are like our active or our modern fires, like the Camp Fire and the Thomas Fire, Tubbs Fire. And not only is it wildly off, but it's wildly off, let's see, in under predicting and over predicting. So it's not a great model, and it can be refit, but we need something stronger. We need a more fundamental theory. Okay, how do we model it? How do we do it at Berkeley? Now, there's a ton of different ways you could do this, and there's seriously tens, if not hundreds, of different models. But this is what ELMFIRE does, and this is what I work on. So the general model overview works like this. We have our basic fuel, weather, topography, and ignition data, like what I showed you earlier, those maps. So we take that FBFM 40 model. We also put in whatever our weather data is at the 2 kilometer level. We're able to solve basic mass and momentum transport equations to simplify that down or rescale it to the 30-meter grid resolution that we run it at. But there's assumptions and approximations that are made during the way. Topography we can take from Google Maps, or there's also databases online, and then ignitions from whatever the report was. We then have 3 pretty distinct sub-modules: the urban spread, wildland spread, and firebrand transport. The urban and wildland spread, originally it was using Hamada and Rothermel. to calculate rates of spread. We've since updated it to maybe better fit equations. And firebrand transport, we're using a stochastic model since we don't know when the structures are going to break in a certain way that forms the firebrands. We have to kind of approximate it. And this requires then that we do something like a Monte Carlo simulation to get kind of the average response that's going to happen. So the firebrand transport creates new ignitions. From here, we get our rates of spread. We use a mathematical model called level set method, which is like a geometric method that I'll talk about in a second, to kind of update the new fire line. So we see, this is a sample from like our tutorial of, you have that spot ignition up at the very top, and then it's spreading a little bit more, a little bit more, a little bit more. These are hourly isochrones. So this would match what like the weather report, or the fire line report would show from like the satellite data. From all of this, we get a lot more information. So we get the hourly isochrones. We also can measure can calculate the fire line intensity. If we're looking at urban environments, we can get the heat flux received. So how hot or how much are my different structures receiving heat. We also get a measure of the number of structures destroyed, how quickly the fire is spreading, so the arrival times, and then also an approximate number on the firebrands generated. And this is actively used. So going back to Pyrocast, not only does it have information on the weather and the fuel moisture, but it also uses ELMFIRE to estimate fire and forecast fire spread. So it uses like a very simplified version of our current model to do this. And it gives like pretty good estimates. I chose the largest 90th percentile. This is one of the fires that's burning right now in I think Washington, sorry. And so this is able to be used by first responders to kind of determine or forecast where the fire is going to be. I think that's pretty cool. So I want to talk a little bit more about the level set model. So this is like the foundations of the model. If we zoom way out, we can kind of ignore a lot of these small scale processes that are occurring. And we see that my fire starts to really just look like this line of some measurable thickness. This is called the fire line thickness. And you can think of it going back to that fire triangle. If there's not enough heat received or there's not enough oxygen or whatever, then it starts to transition into smoldering, which is like a second stage flaming. And then if there's preheating of the fuels up front, then it'll also thicken the fire line. This is approximately, it kind of washes out when you zoom out really well. So this is level set is like this mathematical tracking of the spread. And it was actually created by a mathematics professor here at Berkeley. I think he's still around, Sethian. I don't know if anybody's a math. Okay, he's still around? Very cool. Very cool. You could talk, I think somebody in my lab talked to him about, hey, we actually use the level set model. So this is kind of cool. And it's a nice in-between approach. So we're doing computational modeling that is still using these operational models. So we're fast enough, or we're close to being fast enough. But since this is really providing a nice framework for us to build up as much physics as we want and incorporate as much of those scary equations as we need. This is a pretty simple, this produces a pretty simple partial differential equation. I don't know the familiarity of everybody with differential equations, but this term basically is tracking the fire front and allowing it to change over time, the position. And then these dx and dy terms are the movement of the fire spread or the fire front in the x and y directions. And again, we can calculate those ux and uy from something like Rothermel or some equivalent, where it's really a primary function of the mid-flame wind speed. So how fast is my wind moving really close down to the ground where the fire is, and then also the slope locally. If you notice, fires spread much faster upslope rather than downslope. You can kind of think of it as it's able to touch the fuels or heat the fuels ahead of it a lot faster. Now, something that I'm working on specifically is an enhancement of this. So like I said, we have a very basic structure at the bottom. I want to kind of enhance it by incorporating more physics. Well, I found out in premixed turbulent flame theory, this is like combustion that's happening in your engine now. We also use level set method to model the tracking of that flame sheet. So this is really small scale, and it's called the G equation if you're interested. But this G scalar is equivalent to what we call phi here. And something that it includes is the effects of wind flow, specifically on how our fire front is changing with space. So it specifically includes the bulk flow. So this is like the wind speed locally. And then there's this kind of generalized rate of spread term. Here's a really nice illustration that shows the effects of wind on flames. So you get what's called flame tilt. So when you have airflow, it is creating more oxygen, putting more oxygen concentration locally. So it's allowing better combustion. So it increases the height of the flame because there's more combustion occurring. This also affects the amount of heat release that's available. It's also changing the geometry. And since everything is dealing with heat fluxes, now I have a larger surface area for the heating to occur to my fuels ahead of the fire. And also, like physically, the flame is touching the fuel. So this is now the direct flame contact. So it's literally touching my house now. Now that generalized rate of spread term can be broken down like this. And it looks a lot scarier than it should because I'm bad at choosing variables. But we have this undisturbed or reference rate of spread. This is the same as that initial term in Rothermel's equation. So it's just the ratio of the heat received and then the heat available before starting to combust. But now we're starting to include curvature effects and also, again, the bulk flow effects. Now, this is specific for the normal rate of spread. So if I go back, this is for, this is just in general. And now this specifically is for the normal rate of spread of the surface. I can kind of write this in a nicer manner using these dimensionless numbers called Markstein numbers. So for curvature and for advection. Everything here so far, all I've done is replace the theory for the premixed turbulent flames with now the large scale understanding of what these things mean. Conveniently, what pops out is my fire front thickness, so that length scale, and then also what's called the planar residence time or planar flame residence time. So this means like how long is my flame staying in a specific location. A little bit more about that the curvature effects. So you can kind of think of it as, and this is a better example. This is an actual burn that occurred. When I have concavity here, think of if you're just looking at heat flux normal to the surface, this area here is getting really lit up with our additional heat coming towards it. And so because of that, my fuels are able to spread a lot faster, or heat a lot faster, combust a lot faster. And so my spread locally is much faster than would it be if I am going out more. And so that's what I mean when I say the curvature effects. So that's a little bit about what I'm working on. This is absolutely not exhaustive. We have 5 or 6 people in the Berkeley Fire Research Lab that are working on modeling alone. So this is kind of the big projects that we're working on. So again, improving physics modeling. So how can we improve physics accuracy? We can do this by doing additional numerical studies using fire dynamics simulator at the small scale to inform kind of our input parameters or estimated values at our large scale that we just kind of assume is constant. Suppression and attack modeling. So can I better optimize how we choose our drop maps when the fire is actually happening. Verification and validation. This is, does the model predict accurately, and is it useful? If it's not producing accurate information, then that could be very harmful for our ground troops. Hey, go over here and stop the fire. Oh, there's not a fire over here. Uh-oh. And then code speed up. We're really trying to get this real-time forecast for our high fidelity approach, and not just like the simplified version of the model. That's in the model development. We also have stuff in the application. So how can we better protect communities by informing policy decisions? If you are familiar, there's this zone 0 policy, which is, I hinted to earlier, but it's the clearing of the vegetation in the, what we call the zone 0 of your house, which is like the closest 5 feet from your structure. So removing all of the plants, and maybe if you have cardboard or trash or something like that near your house. That really helps with likelihood of probability of ignition due to the spotting. And then also risk modeling. Can we do a better job of quantifying fire risk and fire hazard, and do a better job of forecasting that every day? I really want to give a huge shout out to the other members of the Berkeley Fire Research Lab. They've been very friendly for the last 5 months that I've been here. And they've really helped me learn a lot about fire, especially when I start to ask very stupid questions. So we're always looking for undergrads. Who is an undergrad? Okay, very awesome, very awesome. We love helpers. We not only do modeling efforts, but we also do experimental. We're like split 50-50. So some very cool projects that we're working on right now, for example, we're doing more of these fundamental studies with firebrands, looking at like the heat transfer that's coming off of them. Also about fire whirls. So this is, and now we're talking about vorticity dynamics and how it's affecting the rate of spread. And then also burning emissions. So when your house burns down, what are the really nasty chemicals that are being produced off of this? And then how is this impacting like our the human health downwind? And then for the modeling projects, hopefully you paid attention. There's all the fun stuff that we're doing there too. But we're absolutely looking for help right now. Especially we're needing help with firebrands. We're looking at the spread of firebrands through like calculating the drag coefficients, these things, so we can model the transport of these better. And that's all I have. So any burning questions? Bad joke. Thank you very much. What's up?
So you were modeling the firebrands.
Yes.
How exactly do you prospect that with the actual, like, for example, the video where you show firebrands? Do you have like some sensor that tracks every single one of them?
Yeah, totally. So they have large metal pans full of water, and they're kind of like tilted at an angle. So as the firebrands come in, they land into the those trays, and they can collect them later and analyze them. And we're talking about tens of thousands of firebrands. And so I feel very bad for all of the grad students who had to go one by one and take a nice picture of it and measure it and catalog. Hey, what's up?
How long does it take to run?
Are you talking about like the fire dynamic simulator with all the equations, or? Yeah. So, oh yeah, sorry. So asking about how long it takes for these high fidelity models. So fire dynamic simulator has a specific wildland fire module where they do like they basically introduce the Rothermel equation and do like really simple elliptical fire spread calculations. And that allows them to run it a lot faster. If we were to truly do the kind of meshing required for good fire dynamic simulator outputs, it would take months, years. I mean, seriously, it really depends. Fire dynamic simulator is great for compartment fires. So like things that are happening in this room. So if like that trash can was on fire, how would that spread to the rest of the room? It's not very well built for these this landscape scale. Thank you. Did you have a question?
Yeah.
Yeah, we're totally looking for across the board. We need help with everything. Specifically, right now, we're only looking for experimental helpers, but in the future, we're also looking for modeling people. So we'll take people from computer science, physics, engineering, obviously, just really across the board. And for example, if you are in maybe like ecology or anything like that, I guarantee you we can find a place for you where maybe you're helping out with better classification of fuels or things like this. Is there any other questions? Yeah.
So it seems like certainly for the real time, also forecasting relies on the data that you're getting from.
Oh yeah.
fires. What are like the main sources of that data? In terms of instruments that collect them, and also what are the ones that the most?
Yeah, that's a really good question. So for the wind data, oh yeah. So where are we getting the input data from? So for the weather, we're getting it from genuinely like the weather stations that are marked in different locations, taking it nothing more than you would get in like your weather report. And then that's at the really high scale, so that we use separate software called Wind Ninja to downscale it to that 30-meter grid resolution. For the vegetation, we're using it's from the website, or it's from the database called ELMFIRE. It's managed by US Forestry Service. And that's like the very colorful map that I showed you earlier. And then for ignition data, we're usually able to get that from the fire chief or something similar. When we're doing hindcasts, it's a lot easier. There's specific fires that we use, especially because there's just, by happenstance, really good data available. So this is especially Tubbs and Thomas Fire. So when we do a lot of our testing, this is what, or like validation of the models, this is what we're using. And it's just, we did a better job of cataloging what happened those days. Yeah. Thank you.
Maybe a quick follow-up.
Yeah.
You said downscale. What does that actually?
Yeah. So in computational fluid dynamics, you require some like input or initial conditions for your differential equations. So we take at the very large scale, you can think of it as almost like a uniform wind condition. And then in solving the interaction of that wind with like drag that's associated with moving through trees and structures and things like this, we can get kind of okay estimates on how that progresses over time or what it would actually look like. But that's a very hot point of content, is how do we get the best weather data? We recently did an input sensitivity study that looks at like how drastically are outputs changing if we change small inputs, and weather or wind data was the most specific. So the most accurate weather data we can get, the better. Took out of time, but if there are any other questions, I'm happy to stay also. All right, good.